Well, here's one of the more complex sections of Lecture 4. We're going to talk about common ion effect and buffer solutions. So the common ion effect, what that is if you have a reaction that is at equilibrium, and then we add, or you can remove as well, but generally we're talking about adding, but add more of one of the species present to a reaction at that equilibrium. So as you add something to an equilibrium, you're going to throw it out of equilibrium, and the reaction has to react in order to restore that equilibrium. Now, this idea of common ion effect applies to all solutions at equilibrium, but for our purposes, we're just going to focus on acid-base equilibria for now. And so if we were to take a solution of weak acid that is at equilibrium, and we add some of a source of its conjugate base to that solution of acid, what we would find is that we're essentially adding a product. And so by adding a product, the reaction says I have too much product now, and it's going to have to shift back towards reactants. And when it does that, it creates a solution that is called a buffer solution. Let's see how this works mathematically here. So let's say that we have a 1 liter solution of 0.25 molar acetic acid. If we measure it or calculate it, what we'd find is that that solution should have a pH of 2.67, and there's the Ka for acetic acid. Now, what if we add a tenth of a mole of acetate ion, C2H3O2 minus? So this is that conjugate base of acetic acid. Okay, so we've added some product in there. Now, according to Le Chatelier's principle, we would predict that this reaction should shift back towards the reactant side. So if this reaction goes back towards the reactant side, we would expect some of the H3O plus to be consumed if the reaction is going to go that way. And in doing so, what we're going to do is decrease the amount of H3O plus, and so we should see an increase in the pH, so that it should become less acidic because we are pushing this reaction towards the left, back towards reactants, if I were to add some acetate ion to the solution. So we could actually calculate this out. We would set up the icebox like this. So we would assume that we're not at equilibrium, and really what we're starting with is 0.25 molar of the acetic acid and 0.1 molar of the acetate ion, and no H3O plus, and then we've got a minus X plus X plus X. We know that the reaction still has to move in the forward direction at this point because I have no H3O plus to start. Now, so I'm going to have a minus X acetic acid, plus X of the acetate, and plus X of the H3O plus. I end up with 0.25 minus X, 0.1 plus X, and X in my equilibrium line there. We can go in and solve this. So we have concentration of acetate times concentration of H3O plus over concentration of acetic acetate right here. That's my Ka expression. We plug in the values from the E line in our ice box, and that has to be equal to the Ka. Again, we have a very small K here, and so we can assume that any K that gets, or any X rather, that gets added or subtracted is essentially too small to matter. And so we're going to ignore the X that gets added here. I guess it's not good to cross out an X with an X, is it? We're going to ignore the X there, and we're going to ignore the X there. We can't ignore the X that's there because that X is multiplying something. Remember what we're doing with the X here and here that we crossed out. Those are X's that are much smaller than 0.25 or much smaller than 0.1. So we'd say that 0.1 plus X is still essentially 0.1, and 0.25 minus X is still essentially 0.25. Now, this simplifies our problem greatly because we end up with 0.1 X over 0.25 is equal to 1.8 times 10 to the minus 5. And what we end up with a value for X is 4.5 times 10 to the minus 5. and you can see that 4.5 times 10 minus 5 is much smaller than 0.25, much smaller than 0.1. It's outside the significant figures, and so if you add or subtract that value here, it will not make any difference to those values to two significant figures out in the second digit there. So our assumption was valid, and so now we have the value of x, which is equal to the concentration of H3O plus, and we plug that into our pH equation, and we find a new pH of 4.35, which was pretty much exactly what we said would happen. We said if we added some of the conjugate base, some acetate ion, we said that the reaction would shift towards the reactant side and that the pH should go up. And we were at 2.67, we're now at 4.35, so our pH did in fact go up. Another way of looking at it is we have an aqueous solution at equilibrium, we added some base, the pH went up. That shouldn't be surprising. Okay, but we would have predicted that again from Le Chatelier's principle as well, so we can actually demonstrate that numerically. Now I mentioned that when you have your acid and you've added some of its conjugate weak base to that solution, we have something that is called a buffer solution. Now we can't have just any amount of a conjugate. We have to have a substantial amount of conjugate present, and we'll see what substantial means here in just a little bit. But when you have a buffer solution, you have a very strong equilibrium between a weak acid or base and its conjugate. And these solutions have the ability to resist changes in pH, even if we add a small amount of strong acid or strong base. And when you have a biological system, which are typically very sensitive to pH changes, this ability to resist change in pH becomes very important. So let's go back to our buffer solution of acetic acid and acetate ion. So here's the equilibrium that we have. We have, or just kind of by convention, we tend to put the parent compound, didn't want that, we tend to put the parent compound, in this case the acid, on the reactant side, and the ion as the conjugate over here in the product side. Okay, so we have that written as a Ka reaction, as an acid dissociation, which makes sense too because we can look up the Ka of acetic acid. We cannot look up the Kb of the acetate ion. That's something we would have to calculate. So it's always best to write it with the thing you can look up going in the forward direction. So that would make more sense when you do a calculation. Okay, so here we've got our solution, our buffer solution. We've got plenty of acetic acid. We've got plenty of acetate ion. If we add a source of strong acid, maybe a little hydrochloric acid, it's a source of H3O plus. Well, H3O plus is going to react with the strongest base present in the solution, and the strongest base present in the solution is our acetate ion right here, and it's going to do it in a 100% reaction. Acid-base reactions tend to go 100%. So here we have the acetate ion reacting with the added hydronium ion to make more acetic acid and some more water. Now, what did that do to the reaction? Well, it was at equilibrium. Then we added the acid, and it reacted with some of the base of the buffer. And at that point, the solution becomes out of equilibrium. Okay, we were right here, and then as I added acid, the amount of acetic acid went up because it got made, and the amount of acetate ion went down because it got consumed. Okay, so I'm now out of equilibrium. So the equilibrium is going to want to restore itself, and it's going to do so by taking some of the acetic acid that was just made and turning it back into acetate ion. Because at that point I have too much reactant and not enough product. So the reaction will shift back in the forward direction. The acid drove the reaction in the reverse direction, and then when all that acid has been consumed, equilibrium is going to drive it forward once more. Had I added some strong base, just the opposite would have happened. The strong base would have reacted with the strongest acid, the acetic acid. That would have shifted the reaction in the forward direction, and then equilibrium would have driven it back. And so what happens is it offsets, whoops, didn't mean to shift yet. There we go. So what happens with these buffer solutions is when you've thrown it out of equilibrium by adding a small amount of strong acid or strong base, then the reaction restores its equilibrium, and it reduces the amount of effect that the addition of strong acid or strong base has on that buffer. Now the calculations for doing those, we saw earlier, lots of things to do, lots of mistakes you can make. But two gentlemen, they're actually biologists, they realized that they were constantly having to ignore that value of x in those equilibrium equations that they were working out. So anywhere that you had x added or x removed, you just tended to ignore it because it was always so small. So they created an equation that you use that assumes that you're going to ignore that x. So the equation itself is an approximation for buffer solutions, and generally it works just fine because more often than not you can ignore that x that they assumed. However, if you have very dilute solutions, then all of a sudden the x that you're ignoring becomes a larger factor, and so this equation can fail occasionally. You won't need to worry about it failing in this class. But this equation is called the Henderson-Hasselbalch equation. And again, it uses the fact that we were constantly ignoring any x's that are added or subtracted in our equilibrium equation and came up with the resulting equation. And so we have pH is equal to pKa plus log of conjugate base over acid. And as you just heard me do, I tended to confuse these a lot when I was in your shoes. What goes on top, what goes on the bottom? Well, always remember, so we have this written as a Ka expression because we're using Ka. And remember, when you have an acid dissociation, you have Ha plus H2O going to our A minus, which is our conjugate base, plus H3O plus. Okay, so we still have products over reactants. So the log term in the Henderson-Hasselbalch equation is still products over reactants, just like our equilibrium expression, and that's where it comes from. Okay, so we have our pH is equal to the pKa, so we take the negative log of the Ka of the acid plus the log of the conjugate base over the acid. So the concentration of the conjugate base over the concentration of the acid. So what does this really mean? It means that the pH of the buffer is controlled by two different things. It's controlled primarily by the strength of the acid right here, that pKa. And then it gets adjusted a little bit by the relative amounts of the conjugate base and the acid that are present in the solution. Okay, so here's an example that we can do. We've got a buffer solution made of bicarbonate, NaHCO3, or sodium bicarbonate, and sodium carbonate, Na2CO3. The Ka for the bicarbonate is 4.8 times 10 to the minus 11. Notice that the bicarbonate has an H, the bicarbonate has an H, the carbonate does not. And so we're going to write it as a dissociation of the bicarbonate ion into carbonate. Notice that we've left the sodium out of it. It's a spectator ion because all sodium compounds are soluble in water. The sodium is going to float away off the solids, and they're not going to play a part in the reaction. And so here's our equilibrium. We've got our acid, the HCO3, the bicarbonate ion, plus water. The bicarbonate is going to lose its H plus to water and form H3O plus. And then what's left over from the bicarbonate is the carbonate ion, CO3 2 minus, as the conjugate base. So we can set up our Henderson-Hasselbalch equation. We're given the Ka for our parent acid, HCO3 minus. We take the negative log of 4.8 times 10 to the minus 11, and we get 10.32. So we need that pKa. And now we can set up our overall equation. So we've got pH is equal to pKa plus the log, and it's going to be products over reactants. Okay, so we have the carbonate ion over the bicarbonate ion. Our carbonate ion concentration was 0.17. Our bicarbonate ion was 0.18. So we have the pH is equal to 10.32 plus log of 0.17 over 0.18. And notice the difference between the pKa and the pH is only 2/100ths of a pH unit. So that's that adjustment made by the ratio of your conjugate base and acid ions present. So it just had a little effect on there. So here's one for you to try. We have a Ka for phenol, and so that's going to be your acid. And then you've got sodium phenolate. That's going to be your conjugate base. And again, notice that it is a sodium salt. The sodium's going to just go away and float around in solution as a spectator. So go ahead and try that one. And here's another one for you to try with nitrous acid and the nitrous ion, NO2 minus, nitrite, sorry. Now we mentioned earlier that if we add a small amount of strong acid or base, we will get a pH change in the solution. A buffer solution resists the change in pH, but it cannot stop it entirely. But it does limit the change by quite a bit. Okay, and when we're doing these kind of problems, after adding some acid or base to a buffer, there's a couple of different calculations that we need to do. The first thing we need to do is the reaction of the strong acid or base with one of the species in the buffer solution, either the weak acid or the weak conjugate base, or vice versa. Okay, so your strong is going to interact with the weak. And then we need to look at the equilibrium of the resulting solution. What are the new concentrations of the species present in your buffer solution? We can now put these into the Henderson-Hasselbalch equation and calculate a new pH. Now, if you're ever tasked with having to make an effective buffer, we can...
on the web for strong is going to interact with the weak, and then we need to look at the equilibrium of...
Sorry, Siri started talking to me.
It's okay. Really?
That's just weird. Okay, so when we are looking at making an effective buffer, what we need to look at is that ratio of base to acid. Remember when we first learned about buffer at the start of this talk, we said we need a substantial amount of the conjugate. And what that means is we have kind of a set ratio. So the ratio needs to be somewhere between 0.1 to 10 of base to acid. So we can't have any more than 10 times the amount of base or acid to the other component in order to be an effective buffer. What that really does is it gives you an effective pH range for a buffer of plus or minus 1 from the pKa or the pKb of your acid or your base. That's how much you can adjust your pH around that pKa and still have an effective buffer. And the higher the concentration of acid and conjugate base, or base and conjugate acid, the higher concentration of both of those that you have present, the better that buffer is going to be, the more effective it's going to be. As the concentrations get too low, they get consumed very quickly, and they cannot offset the addition of strong acid or base very effectively, because if once one of those gets completely consumed, you're going to go outside that 0.1 to 10 range, and then you no longer have a buffer, and the pH is no longer held in check. So we can also use buffer solutions to do pH control. We can use the Henderson-Hasselbalch equation to tell us how to make a buffer solution with a very specific pH. So here's an example. We want to say, what is the ratio of sodium acetate to acetic acid? And we're just going to abbreviate acetic acid as HAC and acetate as AC minus. So we want to make a buffer out of sodium acetate and acetic acid. We want to know what ratio do we need to have that pH be 5. And the Ka of acetic acid is 1.8 times 10 to the minus 5. So we're going to work kind of backwards here. So here's our equilibrium reaction here. We've got acetic acid and water going to hydronium plus the acetate. Since we are given the Ka of acetic acid, we want to write our equilibrium reaction as the acid dissociation of acetic acid, so reacting with water. We have our Henderson-Hasselbalch equation here. And so what do we know? Well, we know the pH. We want the pH to be 5. We can calculate the pKa from the Ka. So if you take the negative log of 1.8 times 10 to the minus 5 there, you'll get 4.74. Plus the log of conjugate base over acid. We don't know our concentrations of base or acid. We weren't told any of that information. Turns out we don't need the concentrations. All we need to know is the ratio of the concentrations. Okay, so when we solve for our ratio of conjugate base to acid, we get a ratio of 1.8. And so what that means is that any molar ratio of 1.8 will give us our pH. Okay, so we can have a concentration of 1.8 molar for our conjugate base and 1 for our acid. That will give us a pH of 5. We could have a concentration of conjugate base of 3.6 and for acid 2. That would give us a ratio of 1.8 and would give us a pH of 5. So it doesn't matter what the concentrations are, just as long as the ratio is 1.8. It will give us a pH of that solution equal to 5. So there we are with common ions and buffer solutions. Some difficult material to take a look at, and if you have any questions, make sure you contact me.